I want you to take. Yes, you can use it. I guess. Hey, so welcome everyone. Let me quickly do this. It is great to have you all here with us. We prepared something quite special for you. I think it is quite a unique topic nowadays, quantum computing. We were really sort of trying to come up with some unique ideas for you, and we came up with that. So I hope this lecture will truly explore this multidisciplinary field of quantum computing and introduce us to something new and exciting. And for that, we invited an amazing Pavel Gura, who is going to talk to you today and explain and introduce you to this fascinating field. So please welcome and give him a warm round of applause.
Yes. Okay, thanks. Thanks for the introduction. Thanks for the invitation. Hello, everyone. My name is Pavel, as Nikita introduced. I'm the founder and CEO of the Quantum AI Foundation, which is a non-profit organization supporting education, research, and collaboration in new technologies, especially quantum computing and AI. And later, at the end of the lecture, I will tell a bit more about this organization. I'm also the coordinator of the board of QWORD, and at the end I will also tell more about QWORD. So QWORD is an international organization aiming to build an open global ecosystem for quantum technologies. So I've been serving as the vice chairperson for several years, and 1 month ago I became the chairperson. And at the same time, I'm also coordinator of QPoland. So QPoland is one of the Q cousins, the so-called Q cousins of QWORD. So in QWORD, we have these local groups in different countries. Currently, we have them in more than 30 countries. And Poland was one of the 5 founding members of QWORD. And we organize lectures like similar to this lecture, or meetups, workshops on quantum computing and programming, and contests, hackathons, conferences. So I will tell a bit more about these opportunities later at the end of my talk, to tell you more about the opportunities that you have if you want to learn more. But first I will start with an introduction to quantum computing. What the quantum computing actually is? So the simple answer is that these are computations according to the laws of quantum mechanics. So in the term quantum mechanics and quantum computing, we have the word quantum. So what does this word quantum actually mean? So in physics, a quantum is the minimum amount of any physical entity or property involved in an interaction. And the fundamental notion that a physical property can be quantized is referred to as the hypothesis of quantization. And this means that the magnitude of the physical property, like energy, can take on only discrete values consisting of integer multiples of one quantum. And we know that our physical world is quantum. We know it since more or less the beginning of the 20th century. The postulate of Max Planck is considered as the beginning, or at least a major milestone in discovering of quantum mechanics. And this postulate says that the electromagnetic energy could be emitted only in quantized form. Like energy is, here we have the frequency of a photon or electromagnetic wave, and there is the Planck's constant involved, and there is an integer number, right? So this energy can be emitted only in some quantized form. So it cannot be an arbitrary value for a given electromagnetic wave. And it has some consequences, because when we think about computations, we can think about algorithms, and we can design new algorithms. We can prove the correctness of algorithms. We can try to calculate the time complexity or space complexity. I believe that you heard about it on the classes, during the classes of algorithms or data structures. But at the end of the day, we would like to implement our algorithms using some programming languages and run our programs on the real physical device. And these physical devices, computers, are governed by the rules of the physical world, the rules of physics. And these rules of the physical world are quantum inherently, and indeed we know it from the beginning of the 20th century. And there are some important consequences. So one of interesting consequences, maybe you heard about it, is a Landauer principle, which says that there is a minimum possible amount of energy required to end a logically irreversible manipulation of information, like erasing one bit of information. And there's this kind of Boltzmann's constant involved. There's the temperature of environment and the logarithm of 2. So if we want to run some computations in our physical world, we cannot do it for free. So this energy, the required energy is not big, as you can see, but there is a minimum energy that we may need to do it. So we cannot do it totally for free. Okay, and so as you probably know, in 40s or 50s of the 20th century, the first classical computers were very big, right? So they were really large devices that occupied the rooms of the size of this room, more or less. So of course the scientists were thinking whether computers can be made smaller. And, currently, you have much more powerful processing units in your mobile devices or in your laptops than we had about 80 years ago. So there was a progress. And Richard Feynman was one of the researchers who was considering whether we can build smaller computers. And he said that there is nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. In fact, there may be certain advantages. And when researchers started analyzing the pace of the progress in miniaturization of the computing elements, there was an observation, it is attributed to Gordon Moore, that the number of transistors in a dense integrated circuit doubles about every 2 years. So currently it is known as the Moore's law. So actually at the beginning this doubling was even faster, about once per 1.5 year. And this prediction proved to be accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. But several years ago, even Gordon Moore himself says that I see Moore's law dying here in the next decade or so. And Intel, the company producing processing units, also realized that this pace of advancement has slowed. So now it's not once per 2 years, but once per 2.5 years, more or less. But this trend will continue. But the question is if the trend will continue forever. So if it will continue for the next years, then about 2035, 2040, the size of a single transistor should be of the size of a single atom. And in such a small scale, the transistors that we know nowadays cannot just work as they work nowadays, because the laws of quantum mechanics will just prevent such operations. So actually, even nowadays, or even about 20 years ago, it has been already challenging. It was already challenging to make this integrated circuit smaller and smaller. So currently, it's really we really need an advanced technology to continue this progress, and it's in some cases it might be just not worth to do it. So it might be just too expensive. But let's assume that our transistor can be of the size of a single atom. So now the natural question is how we could run computations in such a small scale. So Richard Feynman, again, at the beginning of 80s, 20th century, proposed that we can, in principle, make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function, the ones move around, the zeros move around, and finally, along a particular bunch of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant, no losses, no uncertainties, no averaging. But can we do it? So that was the question. And since today we have a lecture titled "An Introduction to Quantum Computing," then I believe that you already know that we are able to build some quantum computers and some quantum processing units. So here is an example. Right? So this is a quantum processor from Google. It's the name is Bristlecone. It has, as far as I remember, it has 72 qubits. So on the right is a cartoon where of this device where each X represents a qubit with nearest neighbor connectivity. And now we have many other quantum processing units developed using different technologies. So we know that we can already build some quantum computers. Okay, but how we can perform computations using quantum computers and how the quantum computers are different than classical computers. So in case of classical computers, the information is represented using bits, and we have classical gates that modify the bits, right? So the bit, a single bit can be in a state 0 or 1, right? True or false. And there might be some classical gates like and or not, if you know them. Which can just take some bits as an input, and then we can produce the output that can be an input to another classical gate and so on. But in case of quantum computers, we have qubits and quantum gates. So what's the difference? So in case of a bit, the set of a bit can be just a value element from the set 0, 1. So mathematically, it's something very simple or relatively simple. But in case of a qubit, the state may be in a so-called superposition of state 0 and 1, which means that it can just carry some information about 0 and some information about 1 at the same time. And I will soon explain how to think about the states of the qubits. Mathematically, it can be a unitary vector, any unitary vector of the two-dimensional Hilbert space over complex numbers. So even the mathematical description or definition seems to be much more complicated. And now the question, who heard about Hilbert spaces? Now what are the Hilbert spaces? No. Who heard about complex numbers? This should be easier. Okay, all right. So that's good. You don't need to know what the Hilbert spaces are. No worries. But do you know what are linear spaces? Matrices. Okay, good. That's fine. This should be sufficient, no worries. So what are the other differences? So in case of bits, the state is determined. So we can know exactly whether the state is 0 or 1, and we can change 0 to 1 and vice versa. But in case of qubits, if we want to get the value 0 or 1, we have to do a measurement of the qubit, which breaks the superposition, right? So after the measurement, we get 0 or 1, and we don't have information about 0 and 1 at the same time. We just have the result of the measurement, 0 or 1. So it can be something like measuring a spin of an atom. And we just have and we can operate on probabilities of getting 0 or 1. And these probabilities depend on the qubit, so on this unitary vector and so on. And our quantum gates may modify the qubit, so as a consequence, they may modify the probability of getting 0 or 1 after the measurement. All right, so now a bit of math. So this is just a representation of a superposition. So this can be a representation of an arbitrary state of a qubit. So here, this 0 and 1 with this brackets that may look strange for you. So by the way, this is the so-called Dirac notation from the name of the last name of the famous physicist of Dirac. And this is also called the bracket notation. So this 0 and 1 are our representation of state 0, 1, but instead of thinking about them as just numbers, 0 and 1, or true and false, as in classical computing, we should rather think about them as unitary vectors, which are an orthonormal base of a quantum system of this two-dimensional Hilbert space. Do you know from the algebra, do you remember from the algebra what is the orthonormal space? Or the orthonormal base? So it means that these two vectors should be orthogonal and their length should be 1 unit, right? Okay, so we can think about them as vectors 1, 0 and 0, 1. Right? So this is our representation of 0 on values 0 and 1. And A and B are complex numbers, right? But they cannot be just arbitrary complex numbers because the squares of their amplitudes are probabilities of getting 0 or 1 in a measurement, so that the sum of the squares should be equal to 1. Right? So these are the probabilities of getting 0 or 1 after the measurement. All right, let's go further. So now just to recall the complex numbers, right? So this is the representation of any complex number. A and B are real numbers. I is imaginary unit, so that I square is -1. So there is a real part and there is this imaginary part. So we can also think about a complex number as a point in a two-dimensional space, right? And then this square of the amplitude is just a squared plus b squared. Okay? So this is maybe not very important, but I just wanted to recall it because then when we think about the vectors that have the length 1, then all these vectors or all these complex numbers are just points on a circle of the radius 1, right? And they can be just represented using just a single argument, just an angle, right? So we need just one value to represent a point on such a circle. And what is important is that it turns out that so this is called the face. It's called the face of a complex number, or also a face of a quantum system, actually. And it turns out that so for both these A and B, these complex numbers, we have some phases, we have these angles, but it turns out that only the relative difference between these phases has any physical meaning and physical significance. So the consequence is that when we multiply those values, those numbers A and B by any other complex number of the length 1, it really doesn't change the physical meaning of the quantum state. So we can think that this is the same quantum state, and actually then we can just multiply both these numbers by complex numbers, such that here we'll have a real number and here we'll have another complex number. So it's not very important, so I just maybe skip it a bit. But what is important is that we can represent our qubits, our quantum states, using such a spherical representation, using spherical coordinates, using just two angles, right? And then we have the cosinus of a single angle, and then we have another angle, and these two angles correspond to a point on a sphere that is called the Bloch sphere, which means that you can think about the qubits or states of qubits as points on a sphere, right? So in classical computers, the states can be 0 and 1, so they can be just antipodic points on a sphere, all right? But in quantum computers, the state can be any point, any arbitrary point on a sphere, right? Yeah, we can see already that there are infinitely many possible states of a qubit already. So sometimes quantum computing or using a single qubit is also called the journey on a Bloch sphere, because it will, as you will see, the quantum gates correspond to rotations of the sphere. Right? So when we have a single point on a sphere, then we can calculate what's the probability of getting 0 and probability of getting 1 after the measurement. And then when we apply a quantum gate, we make a rotation of the sphere around one of the axes, and then we modify the probability of getting 0 or 1 after the measurement. Okay. And these are just some notable examples of the quantum gates. One of the most popular quantum gates is called the Hadamard's gate. So I'll tell a bit more about it, but it just transformed the point 0 or the vector 0 into the superposition of state 0 and 1, such that the probability of getting 0 and 1 after the measurement is the same, is 0.5. And X Pauli gate, it transformed the state 0 to state 1 and 1 to 0, which means that this is a quantum negation, basically, right? And there might be some parameterized rotations. There might be also quantum gates operating on more than 1 qubit, like 2 qubits. So CNOT is a notable example because here the 1 qubit is a controller for the node, so this X Pauli gate operation on the second qubit. And these gates are actually sufficient. So, of course, there are many other existing quantum gates that we can potentially build to make our computations more efficient. But it's good to know that any quantum circuit can be simulated to an arbitrary degree of accuracy using a combination of this CNOT gate and single qubit rotations. So we have these rotations. And now a bit more about the Hadamard's gate. So as I told you, the state 0 is transformed to the superposition of state 0 and 1, and 1 also to another superposition of 0 and 1. And it turns out that this Hadamard's gate represents a rotation of 180 degrees around the axis x plus z on our block sphere, right? So let's go to our block sphere. So this is this axis here. And we just rotate around this axis, or alternatively, it's just a combination of rotation of 90 degrees around the y-axis and then 180 degrees around the z-axis. And it also turns out that since we can think about 0 and 1 as vectors, which are the base of our two-dimensional Hilbert space, which is also linear space. And these vectors are transformed to some other vectors. Apparently, this transformation has to be always a linear transformation. So there is a matrix corresponding to the linear transformation. So that, as you remember, 0 corresponded to the vector 1, 0. So in order to calculate how the vector 0 will be transformed, we just have to multiply this vector 1, 0 by the Hadamard's matrix. So this is the Hadamard's matrix. And then we get another vector in this two-dimensional space. And we can just represent this, this new vector using our two vectors that are the basis, right? And then we get this transformation, right? So we only need to know the Hadamard's matrix, actually. And this is also the graphical representation of the Hadamard's matrix in a quantum circuit. And this is also the matrix for this X Pauli gate, that is our quantum negation. And this is the name is X Pauli because it turns out that it is a rotation of 180 degrees around the axis X on our block sphere, right? So once again, so now we rotate around this X axis. Okay, and so we may have parameterized rotation. So here is a parameterized rotation around the y-axis, and this is the matrix of this operation. And this is the CNOT gate operating on 2 qubits. So if you build quantum gates operating on n qubits, then the corresponding matrices of linear operations should be of the dimension 2 to the power of n. Because then we are in 2 to the power of n dimensional space, and because we have 4 possible vectors being the basis of the linear space in which our vectors are. So this quantum gate acts on 2 qubits and performs the NOT operation on the second qubit only when the first qubit is 1. And otherwise, it leaves it unchanged, right? So that's why it's similar to the identity matrix, but so here's the identity matrix, but if the first vector is the first qubit is 1, then we apply the negation, right? So this is a matrix, a part of the X Pauli gate matrix. All right, and as for now, you have seen the quantum gate for just a single or 2 qubits, but the true power of quantum computing comes with multiple qubits, right? When we have large number of qubits, right? Because when we have n qubits, we can potentially prepare superposition of all possible 2 to the power of n states, right? So we can just apply these Hadamard's gates to all n qubits, and then we have the superposition of 2 to the power of n states, and then we can apply some other quantum gates, and then these quantum gates can operate on all these 2 to the power of n possible states at the same time, and this quantum gate just modify the probability of obtaining each of these 2 to the power of n possible states after the measurement. So the idea of quantum algorithms is to build such quantum circuits to ensure that the probability of getting the result that we want is maximized, right? So that's the goal basically. And this is the example. So here we have 8 qubits. Initially, all these qubits are in the state 0. For qubits 3, 5, and 7, we don't apply any quantum gates. We just perform the measurement. So with probability 1, after the measurement, the results for qubit 3 is 0, the result for qubit 5 is 0, and the result for qubit 7 is 0. Here, for qubit 6, we apply the X Pauli gate, so our quantum negation. So initially, this qubit was in a state 0. We apply the X Pauli gate, so it should be in the state 1 with probability 1. So after the measurement, we should obtain 1 here. And the funny thing is happening now with qubits 0, 1, 2, and 4, because here we have the Hadamard's gate. So initially we're in the state 0. So after applying the Hadamard's gate, this is a superposition of states 0 and 1. The probability of getting 0 and 1 after the measurement is 50%. And then this qubit 4 works as the controller for qubits 0, 1, and 2, because we have 3 CNOT gates here. And then we also apply the negation at the end. So what is the consequence? The consequence is that when we do a measurement here, the measurement of the qubit 4, we will get the result 0 in 50% of the cases, and the result 1 in 50% of the cases, at least in theory, because in practice it might be different, but I'll tell about it later. And because of this, the so-called quantum entanglement, or entangling the qubit 4 as a controller of qubits 0, 1, and 2, if the result of the measurement here is 0, the result of the measurement here, here, and here, from 0, 1, and 2, will be 1, always. Yes? And on the other hand, if the result of the measurement for qubit 4 is 1, then for qubits 0, 1, and 2, the result will be 0, always. So as a consequence, when we run the circuit, evaluation of the circuit many times, like 100 times, we'll observe that in 50% of the cases, we will get a result. So here, starting from, so this is 0, 1, 2, so actually this is 0, 1, 2, 0, 0, 0, 0, 1, 0, 1, 0, and in other 50% of the cases, going from the left here and from the right here, 1, 1, 1, 0, 0, 0, 1, 0, right? And this is just an ASCII representation of my initials, right? P and G. Everyone can do the same thing with your initials as an exercise. So this circuit, quantum circuit, was prepared using IBM's quantum experience framework that is available online. So I encourage you to build a similar circuit for your first letters of your first and last name. So we used 8 qubits to represent 2 8-bit numbers at the same time. So this is something that is not obvious, because for classical computers, by default, when we have n bits, we can process only 1 n-bit number at the same time. But when you have a quantum computer, when you have n qubits, we can potentially process all 2 to the power of n n-bit numbers at the same time. So here you should already observe that there is a potential for some advantage of quantum computers, right? When we can process an exponential number of possible values at the same time, it seems that there might be a potential for advantage of quantum computers over classical computers. But there are also some other differences. So in case of classical computers, the results are deterministic. So even if we have a randomness, so this is actually a pseudo-randomness. So we have generator of pseudo numbers. And in case of quantum computers, we may have real randomness and easily sampled from probability distributions that can be difficult for classical computers. So here with this real randomness, I would like to put a star because actually this is rather scientific, but also a bit of philosophical question what actually the randomness is in our real world, because there are different interpretations of quantum mechanics, and according to some interpretations, we live in the world that is fully deterministic. So there are just multiple worlds existing in parallel. So we still are not sure what actually the real randomness is, but using quantum computers, we can achieve the randomness that really, or that exists in our physical world, and not the randomness generated using some pseudo-random number generators. All right, and there might be some interesting applications of such quantum computers. It's good to know that at least currently, or it seems that quantum computers will not be suitable to run some applications or play computer games, but it's good to know that there are also some quantum games if you are interested. These are educational games. But there might be some other applications, and I will present some of them. So breaking some classical cryptography algorithms using Shor's algorithm. So I will tell a bit more about it soon. But also, we can improve the quantum cryptography, right? Because when we have these generators of real randomness, and potentially we can build better generators of random numbers. And I know that in cryptography there are some attacks that are based on the fact that some generators of random numbers are not perfect, that they're in fact generators of pseudo-randomness and not the real randomness. Solving combinatorial optimization problems. So these kind of problems are almost everywhere in machine learning, AI, finance, transport, logistics, energy sector. Almost everywhere you have optimization problems. Something from difficult distributions, right? So for example, in machine learning, there's also something like a Boltzmann distribution. And as I said, there might be some quantum random number generators. Simulating quantum processors, it may have applications to discover some new materials, new drugs, and so on. Generating art, especially when you have these quantum random number generators. Searching for elements in databases. There's an algorithm that is called the Grover's search algorithm, and it can give us quadratic speedup comparing to classical computers. It's also good to know that there might be some other applications of other quantum technologies. So quantum computing is not the only possible application of quantum mechanics in technology, because we may also think about the quantum communication, and there is something like quantum key distribution, right? So it's good to know that there are some methods for sending information in such a way that you cannot guarantee that this information will not be read by someone who wants to just read your message by the adversarial agent. But if someone reads your message, then you will know it with 100% of certainty that someone has just read the message that you sent, and then you can potentially send another message again. So this is good for the key distribution, when you just want to send a key to another party, to a key that can be used to encrypt some other messages, right? So you want to be sure that no one is able to read it, and if someone reads it, then you will know and you'll be notified with 100% accuracy. There's also something like quantum metrology, quantum sensing, so just to do better measurements in this micro quantum scale. Okay, so now a bit more about this breaking contemporary cryptography algorithms. So the problem is that most, or at least some of the popular cryptography algorithms work based on the assumption that the problem of factorizing numbers is difficult for computers. So as you know, multiplying two n-digit numbers is relatively easy. Everyone can do it in n squared. It's good to know that there's also an algorithm that can do it in n log n. So it's quite a recent result actually. But factorizing n-digit numbers is difficult. Or at least it seems to be difficult because no algorithm has been published that can factor all integers in polynomial time. So there are some algorithms that can do it for some integers, but not for all integers. But what is, for me, even more interesting is that neither the existence nor non-existence of such algorithms has been proved. It's generally suspected that such algorithms do not exist, and the problem is not in the class of problems that can be solved in polynomial time on a classical computer, but it hasn't been proven yet, or at least we are not aware of such a proof. The best published asymptotic time algorithm is the general number field sieve. So here you have the time complexity, so it's exponential or sub-exponential, but for sure it's more than polynomial time. But we also know that in case of quantum computers, we can do it fast. And there is an algorithm that's called the Shor's algorithm, which can factorize any arbitrary integers in polynomial time. So actually, this is a hybrid algorithm in which we have a quantum subroutine responsible for finding a period for a long sequence using the inverse quantum Fourier transform. So that here we have this inverse quantum Fourier transform. So this is quite advanced algorithm, I would say, and there can be even just dedicated lecture about the Shor's algorithm, but I encourage you to just read more about it or watch some video lectures. There are some video lectures of Professor Peter Shor, who discovered this algorithm in the 90s. Yeah, okay. Some other applications, solving combinatorial optimization problems. So in combinatorial optimization problems, we search for the best of many possible combinations. So these problems include scheduling challenges like, should I ship this package on this track or the next one? Or what is the most efficient route a traveling salesperson should take to visit different cities, right? So here we have the traveling salesman problem, which is considered, or which is known to be NP-hard. But it turns out that physics can help solve these sorts of problems because we can frame them as energy minimization problems. And a fundamental rule of physics is that everything tends to seek a minimum energy state. Objects slide downhill, small things cool down over time, and this behavior is true in the world of quantum physics as well. And there is an approach that's called quantum annealing that can take advantage of this phenomenon. But to understand what the quantum annealing is, it's first good to tell about something that's called adiabatic quantum computing. And first explain what the word adiabatic actually means. You might remember it from some classes of physics or chemistry. So an adiabatic process is a process that does not involve the transfer of heat or matter into or out of a thermodynamic system. So energy is transferred to the surroundings only as work. And there is an idea for something that is called adiabatic quantum computers. And there is the word Hamiltonian here. So you can think about, so Hamiltonian is a concept from quantum mechanics, but here for the purpose of this lecture, you can think about the Hamiltonian as a function that takes quantum state and returns the energy of this state. Okay, so first we prepare potentially complicated Hamiltonian, so potentially complicated function, whose ground state, whose global minimum, describes the solution to the problem of interest. Right? So we need to find such a function. Then we prepare a system with a simple Hamiltonian, so it can be just a superposition of all possible states, as we observed in several slides ago. And we can perform adiabatic evolution of this simple Hamiltonian. For example, in practice, it can be done by modifying strength of a magnetic field to the desired complicated Hamiltonian. And then there's something like an adiabatic theorem, which says that the system should remain in the ground state. So at the end, the state of the system describes the solution to the problem. So what's going on here? So first we prepare a function that is relatively simple, so we can easily find the global minimum of this function. We encode it in a real physical device. We perform some operations like changes of the magnetic field. And if we do it according to this adiabatic evolution, in such a way that at the end we get a quantum state corresponding to the function describing our optimization problem, then at the end we should find our system in a state corresponding to the global minimum of this problem. So in some sense, we force the nature to perform computations for us. We don't tell the nature, do this step, this step, this step. We just use the fact that we have the laws of physics. So if I draw something here, then at the end it will be in the, let's say, at least in the local minimum, right? Because of the gravity. So the gravity can perform these computations for me. So I don't have to calculate the trajectory of the object, but I can just do this experiment and I will see what will be the result, right? So this is similar, right? So the nature, the physics can just perform these computations for us. And what is interesting that this adiabatic quantum computing has been shown to be polynomially equivalent to this conventional quantum computing in the circuit model that I present to you at the beginning, with these quantum gates, Bloch sphere, and so on, so that we can just transform one system to another in polynomial time, so we can do it quite fast. This is interesting as well. Okay, but how to do it in practice? So I will give you an example which is interesting and relatively simple, I think. So the reason why we can do something like this is the fact that our world is designed in a way that it is. So, for example, in statistical mechanics, in ferromagnetism, there is a concept of the Ising model. So, in these Ising models, this is a model of ferromagnetism, and we might have some atoms which have some spins, or there might be some magnetic dipole moments, and the spins may correspond to the values +1 and -1. And then, so each atom may have one of these two spins, right? And then when we calculate the energy of such a system, then there is, this energy is expressed in such a way, right? So here there are some coefficients corresponding to the coupling strength, so how strongly some atoms are connected and or interact and so on, right? So here we have some binary variables. And now in computer science, we have something that is called QUBO, quadratic unconstrained binary optimization problems. So in this case, as you can see, we also have binary variables, this time corresponding to 1 and 0 values. And here we have some coefficients, right? So this is just a polynomial of multiple binary variables of degree at most 2, actually, right? Because, yeah, this is the degree at most 2. And there is a correspondence between this QUBO formulation and the Ising model. Here we have also some binary variables corresponding to +1, -1, and we have some coefficients. So if we can represent our optimization problem as the problem of minimizing such a function, then we can encode this problem in a ferromagnetic, and then the energy of such a system would correspond to the values of our objective function for which we want to find the minimum. Okay, so and then as I said earlier, first we can start from a quantum system for which that we can easily prepare and for which we know the ground state, so the global minimum, and then we change the strength of the magnetic field to end up in a ground state that would be a solution of our problem. So now someone may okay, and we can do it by modifying the strength of the magnetic field, right? And now someone may ask, okay, so does it mean that we can solve all kind of optimization problems like NP-hard problems? maybe we can solve NP-hard problems, right? Maybe if we are able to find such a QPOW formulation for the NP-hard problems, maybe it will be possible. But actually, it is an open question. But currently, scientists think that it will not be possible. And there are many problems with this. So first of all, in order to ensure that our system stays in the global minimum, we should change the strength of the magnetic fields low enough. And in practice, this speed, there are some equations, there are some formulas telling us how slow we should do it. And unfortunately, the speed is a function of the distance between possible solutions, or let's say the global minimum and the next best solution, basically, right? And for NP-hard problems, and this distance is relatively low, so we should really change the strength of the magnetic field very slow, and most likely there will be no advantage. But there is some hope, because even if we change the strength of the magnetic field a bit too fast, we cannot guarantee that the system will stay in the global minimum. But it can still be found in a state that is quite close to the global minimum, right? So we can rather think about it as another heuristic, able to find some approximate solutions to our optimization problems. And this is also possible thanks to the process that is called quantum tunneling. So this is also something that just doesn't appear in classical computing and classical mechanics, right? So when so initially we prepared this simple Hamiltonian, and then by changing the strength of the magnetic field, we change the landscape of the Hamiltonian. So here we have the configuration of different quantum states, and here we have the values of the Hamiltonian. So when we change this landscape, and let's assume that even if at the beginning we are here, so that was the global minimum, if after the changes the global minimum is here, our quantum system may just perform something like a thermal jump. So magically, we can just go from here to here. So it's also not possible in just classical optimization using gradient descent, for example. So we'll stuck, in case of gradient descent, we'll stuck in this local optimum if we do the optimization. But in quantum mechanics, in theory, it is possible, but again, in practice, it's difficult, and it doesn't necessarily work. So at least there are still some controversies. There are still some controversies because there are some approaches to employ this quantum annealing, and there's a company from Canada that's called the D-Wave. And they built something like quantum annealers to perform such computations. So it's not a science fiction. You can see that even several years ago, there was an article presenting how to optimize the routes of the fleet of taxis in Beijing. So this is the paper. So it's relatively easy. So I also recommend you to read it if you have time. It was prepared by researchers from Volkswagen and D-Wave. And first they just took a real neural network, and they also have real routes from GPS data. There was a data set called T-Drive. It was a data set of routes of taxis in Beijing from the city center to the airport. So for each taxi, there was just a single route. And then for each car, they added two possible alternative routes between the same source and the same destination. And it was assumed that cars may share road segments. And there was also an assumption that the travel time is proportional to the function or square of a number of cars on a route. So this is a simplification, but it's still quite close to reality. And now we want to minimize the total travel time. So how to do it? So this is relatively simple. So I will present it. So first we introduce binary variables q, I, j. And we assume that the value of such a variable is 1 if car I takes route j, right? So remember, for each car we have 3 possible routes, but we want each car to select exactly 1 route. So this condition should be satisfied, right? For each car I, this term should be equal to 0. Okay, and now let's assume that PS is a set of these variables associated with roots that share street segment S. So this is our cost function, right? So for the street segment S, we just take all the binary variables corresponding to this segment, for which the root just passes through the segment, and the number of values 1 here corresponds to the number of cars traveling through this road segment. And we assume that the total travel time on this road segment is proportional to the square of this number of cars, right? So that's why we have it. So this is the total cost of travel through all the road segments in our road network. This is something that we want to minimize. Okay, but we want to minimize it. But if we just focus only on minimizing this cost function, then the solution is obvious, right? So we just put the value 0 for each variable. But then this condition is not satisfied because we wanted each car to select exactly 1 route and not 0 routes. So we have to add this term, right? So this is just a sum over all cars, I, all right? And now the value of this parameter lambda should be set big enough to ensure that if our solver, classical or quantum, it can be also classical solver, finds a solution or minimum value for this formula, then this part should be equal to 0. Because otherwise, if just a single, in a single bracket for a single I, this value is greater than 0, then if we multiply it by a large value of lambda, it would not be the optimal solution, right? So there should be some better solutions with better cost and satisfying this condition. So this is a standard procedure how to build such formulas. And as you can see, everywhere here we just have our binary variables in a degree at most 2. So it can be represented as a QPO, quadratic unconstrained binary optimization. So it can be encoded in a ferromagnetic. So it can be potentially solved using quantum annealer. And this is what those researchers did. They ran it on the quantum annealer from D-Wave. And this is the solution. So they run experiments and data set with 418 cars. So there were 3 times more logical variables, right? Because for each car, we had 3 variables corresponding to 3 possible routes. So the space of possible solutions was astronomical. And as a result, they achieved a relatively small number of streets that were heavily occupied. So this is the result in the real traffic. And this is the result of just applying this quantum annealer to find a good distribution, good assignments of routes. So it's better than the real traffic, and the time of computations was 22 seconds. But the only or the main problem with this article is that the authors really didn't make any comparison with some other classical algorithms. So I'm pretty sure that there exist some classical algorithms like genetic algorithms or simulated annealing, particle swarm optimization, or maybe some other optimization algorithms, classical optimization algorithms that should be able to find similarly good solutions in a similar time or maybe faster. So it's not a demonstration of quantum advantage or quantum supremacy, but it was a demonstration that the existing quantum computers can already perform some useful computations, right? So this is a useful application for sure. It doesn't mean that classical computers cannot do it, but it means that quantum computers can already do something useful, let's say. So there might be similar optimization problems in logistics. There are some logistic companies interested in such solutions, even in Poland. It's also good to know that there are some works aiming to enhance machine learning, classical machine learning using quantum computers. So I have already read some research articles trying to enhance almost or all possible classical machine learning algorithms with some quantum layers or quantum approaches. So actually, as you probably know, machine learning is almost all about optimization. When you train neural networks, you basically solve an optimization problem. You just want to find the weights of the connections between the neurons in your neural network in order to minimize the loss function. So this is well-defined optimization problem that is classically solved using backpropagation algorithm and with acceleration using GPUs, but potentially those kind of problems can be solved using quantum computers in the future. So almost everywhere we have some kind of optimization in machine learning. And besides applications of quantum algorithms to enhance classical machine learning algorithms, it's good to know that there might be also the opposite approaches when classical machine learning can be applied to improve some of our quantum systems, and there are also works about it. Okay, it's good to know that there is an observable progress in the field of quantum computing. At least from 2017. Earlier, we were also able to observe some progress, but it was not as fast. And currently, it's still not as fast as the progress in AI. So it's an order or maybe 2-3 orders of magnitude of difference in the speed of the progress, of course, but we can observe the progress, right? So even last year, the IBM announced that they have a quantum computer with more than 400 qubits. They announced the quantum supremacy. They published a paper demonstrating it as well. Yeah, but it's good to know that the contemporary quantum computers are still noisy. So we live in the so-called NISQ area. NISQ stands for Noisy Intermediate Scale Quantum. So, which means that our contemporary quantum computers are still relatively small. So they still don't have really large number of qubits, and there is still huge noise in the computations. So when we apply some quantum gates and we perform measurements, usually the results are different than what we would expect and what is given by the theory. So there is a noise. There is a noise, and there are some ways. There are also some approaches to mitigate the noise and to correct the errors of computations. So this is the paper from IBM from the last year, and they also claim that they achieved quantum supremacy. You might remember that several years ago, Google also claimed that they achieved something like a quantum supremacy as well. It's good to know that there are several approaches to build quantum computers. So here I listed only most popular, but it doesn't mean that they are the most promising. There are ion traps, superconducting qubits, Hotelling qubits. There's this D-Waves machine, so adiabatic, let's call it adiabatic quantum computer. There's something like neural atoms or Rydberg atoms. There are approaches, I think that this is explored by Microsoft mostly, to build topological quantum computers. But as for now, and as far as I know, in all of these approaches, there are some serious technological challenges and issues. So it's hard to say which of these approaches will turn out to be successful. And it is even possible that in the future, there might be some totally different approaches to build quantum computers that will be more efficient than the existing approaches. So this is still work in progress, and there are many companies trying different approaches. So how the future may look like. So there is a famous quotation, I think, attributed to Lincoln and several other people, that the best way to predict the future is to create it. So it's good to start working in the quantum computing field, to do research in this area, because there are still many open problems. So some of the obstacles on the road towards quantum supremacy. The coherence. So there is a limited duration of a quantum state. So limited duration of time in which you can keep the quantum state in a superposition, for example, before the measurement. So that because the measurement can be done by any interaction of a qubit with the environment. So that's why this physical qubits should be isolated from the environment, but we cannot do it for a long time. There is a noise, so there is a need for error correction and error mitigation. There is a need for algorithms and proofs, actually, because in many cases it's even difficult to prove that quantum algorithms are better than classical algorithms. Even for the Shor's algorithm, we're saying that we cannot, or we don't know any proof that that classical computers cannot factorize numbers in polynomial time. We just expect that such a proof doesn't exist. And there are some technical challenges, like building some quantum gates is still challenging for several technologies. Now a bit more about this quantum error correction. So I told you that Peter Shor discovered this factorization algorithm, and he also proved that quantum error correcting codes exist. It was also proved a year later that these codes could theoretically push the error rates close to zero, so that we can really correct any errors that may appear due to the noise. And this discovery convinced people that the scalable quantum computing should be possible at all. So this was said by Scott Aronson, famous researcher from University of Texas. And that is merely a staging problem of engineering. So it's not no longer a research problem, but it's rather engineering problem how to do it, because currently, in order to build a single logical, fully error-corrected qubit, we really need large number of physical qubits to do it. So this is one example of quantum error correcting codes, right? So we can just encode just this quantum state 0 as using 3 qubits 0, 0, 0, and similar for the qubit 1. So if we assume that at most 1 qubit among those 3 qubits suffers a bit flip due to the error, then we can easily reverse the errors, right? So the result of measurement is 1, 0, 0, and we know that at most 1 qubit was flipped, then we know that it should be 0, 0, 0 here, right? So this is clear. So this is just example, but it works under the assumption that at most 1 qubit suffered a bit flip. But in practice, it can be more complicated. So it's not that easy, unfortunately. Okay, and I also told you that it's difficult to prove that quantum algorithms will be better than classical. So I gave you an example of a Shor's algorithm, and here's another very interesting example that may be also an inspiration for some of you. Several years ago, the same Professor Aronson, who said that building quantum computers is just a staggering problem of engineering, had a really brilliant student, 18-year-old Ewing Tang. I think that she was already doing PhD studies at that age, so she's really a mathematical genius. And he gave her a task to prove that there's something like a recommendation problem in quantum computing, in classical computing as well, also in computer science in general. It was known that there is a polynomial time quantum algorithm for this recommendation problem. And for many years, researchers believe that there is no polynomial time algorithm for classical computers. So there was an expectation that it can be one of the examples of this quantum supremacy. So Scott Aronson gave this task to this brilliant student to prove it. She was thinking on this, spent some time and months on this problem, and she analyzed the quantum algorithm, and she discovered that actually this problem can be solved in polynomial time using classical computers. So it was discovered after really many years of believing that this problem cannot be solved in polynomial time on classical computers. And the classical algorithm was inspired by quantum and the quantum algorithm. So we didn't prove that there is a quantum supremacy in this case. But anyway, even work on analyzing the quantum computer and work in the quantum computing domain resulted in a significant achievement in the field of classical computer science as well. Yeah, but as I told you, currently we live in the area in which our quantum computers are still noisy, so there are also some frameworks, programming frameworks like CirQ from Google to deal with it. So one of the approaches to deal with it is based on something that's called variation quantum algorithms, which is also considered as an example of quantum machine learning as well. So the idea is that here we have a quantum circuit in which some quantum gates are parameterized. So I present you at the beginning that some quantum gates can be parameterized. And these parameters may also correspond to some parameters of our, say, optimization problem. And then we can perform computations many times, run the circuit, do the measurements, and then average the results. We have some results. And after we get the results, we may apply some procedure to generate another set of parameters for the circuit. And it can be applied to some optimization problems. So this is one thing. And another thing is that even in case of a noise, in this case, it's not a big issue, because when we run the computations many times and then average the results, it's not a big problem for us. And actually, some researchers even think that when we apply such techniques to just train some machine learning models, then the noise can actually help in training, because it may help us escape from the local minima during training. So there are some, let's say, approaches to use quantum computers even with the noise, and there are some, let's say, there are some reasons to believe that the noise may help us solve some tasks, but whether we can simulate this noise on classical computers is another thing. And actually, this is related to what I said. So this was this example of the paper claiming that we've achieved quantum supremacy. This is a paper from Google, 2019. It was published in Nature. So here, just researchers from Google proposed a problem of sampling from a quantum circuit, basically, right? And then, so they build a quantum circuit, and they claim that the distribution that can be achieved by just running this quantum circuit on a quantum computer cannot be simulated or generated using existing classical computers, even supercomputers. Then there were some disputes whether it was really a demonstration of quantum advantage or not, but later there were some other papers also claiming the quantum advantage. So currently, I think that there is a scientific consensus that we know that we've already demonstrated that quantum computers can, even existing and noisy quantum computers can compute something faster, better, more efficient than even the best classical computers that we have. But all these problems in which there was such a demonstration are rather artificial problems and not very useful in practice yet. But in the future, we'll see. So now a bit more about some programming frameworks. If you want to learn, one of the popular frameworks and libraries is Qiskit, so it's a Python library. And actually, most of the existing frameworks and libraries for quantum computing are for Python. So there's another one, PyQL. So this is from a startup that is called Rigetti. It's Project Q, an open source project developed at the ETH in Zurich. D-Wave Lib, so this is this framework for running quantum annealing and solving the combinatorial optimization problems. YAO.jl, if you know Julia, I also recommend you to check it. So Julia is a quite modern programming language suitable for running parallel computation. So this is also one of the reasons why it's quite good for simulating run of quantum computers and quantum algorithms. YAO.jl is a Julia library for quantum computing. There is a framework that's called Pegadain from a company from Canada that's called Xanadu. So it was the first framework for quantum machine learning. So that's why it was called TensorFlow of quantum computing. Before Google released TensorFlow Quantum, so a quantum version of its TensorFlow framework. There's also machine learning library for Qiskit as well, Qiskit ML. All right, and now at the end, I would like to tell you a bit more about the ecosystem of quantum computing and quantum technologies that we are building in QWORD and here in Poland, so that if you are interested, you can also get involved and learn more. So QWORD is a global network of individuals, groups, and communities collaborating on quantum education and implementation of quantum technologies. So it started several years ago, and we focus on educational activities. So we collaborate together internationally to prepare educational materials for quantum computing. And we offer some quantum programming and computing workshops, like Bronze is our introductory level workshop. So people can participate and then they can do some tests at the end and get certificates. So these numbers are not up to date. So we have already handed out more than 10,000 certificates worldwide, more than 400 here in Poland. So here in Poland, we've organized 8 workshops, and worldwide, we've organized more than 130 workshops. Yeah, so I also invite you, first of all, to just take these courses and also to get the certificate if you are interested, and also in help, join us and help in preparation of this educational materials that maybe later in the future will be used here at this university or other universities worldwide to just conduct academic courses on quantum computing. We also organize some hackathons. So here in Poland, we've organized 3 hackathons on quantum games, developing quantum games. So usually these are educational games, computer games, aiming to popularize quantum computing and give people some intuitions how quantum mechanics and quantum computing works. We also organize some research activities. So there is a project that is called Q-Intern. So last year it was 3rd or 4th edition already. Most likely there will be the next edition this year. So this is another interesting and, in my opinion, innovative idea. So first, the senior researchers from all over the world apply and propose some research ideas. And then the students from all over the world apply to be interns guided by the senior researchers. So last year we had more than 500 applications from all over the world. And then we match them. So actually the senior researchers select the students with whom they would like to collaborate during the summer, and for several weeks they work together. And in some cases in the previous editions, such collaboration resulted in scientific publications or some interesting results. Yeah, so if you are interested in research activities and preparing some scientific articles, do some science in quantum computing, this is probably one of the best programs. So we organize it because we observe that in many countries there are not many quantum researchers or students interested in quantum computing, so it's better to collaborate globally. So we collaborate globally, but also operate locally. So in many countries, we have local groups that are called Q Cousins. So here in Poland, we also have Q Poland. So actually, Q Poland was one of the 5 founding members of Q World. And currently, we have these local groups in more than 30 countries. So if you know people, I know there are some people from other countries originally. So if you know some people in your countries who need to establish a new Q cousin, feel free to contact us and can help with this, of course. So here in Poland, we have this Q Poland group. I'm the coordinator. We have about 20 active members now. We release a monthly newsletter that is called Q Poland newsletter. We organize this workshop. So I said that we've organized 8 workshops on quantum computing and programming and handed out more than 400 certificates. So yeah, you can just join our Facebook group or follow us on Facebook, on Twitter, join our mailing list, or follow our website, subscribe to our newsletter, join our Discord. So there are many opportunities to stay up to date. And behind Q Poland, we have the Quantum AI Foundation, which is this non-profit organization, charity organization that they founded several years ago, so in 2019, so almost 5 years ago already, with the aim to support education, research, and collaboration in new technologies, especially AI and quantum computing. And one of the events that we organize as Quantum AI Foundations in Poland is the meetup that is called Warsaw Quantum Computing Group. So we started already more than 5 years ago in November 2018, close to the 100th anniversary of gaining independence by Poland. We organize these meetings more or less once per month. Currently, so after the pandemic started, most of the events are online only. But as you will see, the next event will be on-site stationary. So you can also subscribe to our YouTube channel and Twitter, Facebook profiles, and so on. And have mailing list, LinkedIn profile, and so on. And I already would like to invite you. Oh, something. So work here. Well, I would like to invite you to our next meetup that will be on April 14th. So actually, this is the World Quantum Day. The reason is that 4.14 is the number corresponding to Planck's, or the beginning of the Planck's constant in some units. So that's why this day was selected as the World Quantum Day. Mateusz Staszewski, a researcher from Warsaw University of Technology, will give a talk about quantum architecture research. So it's also some kind of quantum machine learning. All right, and that's all from my side. So if there are any questions, I'll be happy to answer, and maybe just a few more links at the end. If you want to learn more, there are some resources to learn more on the website of the Quantum AI Foundation. I think there are about 20 links. Yeah, I think that's all from us. So if there are any questions, I'll be happy to answer. Yes?
Do you think quantum computers will be widely available?
They're already available, but the question is when they will really give us some practical business advantage. And for this question, it's really difficult to answer. Because I'm not a physicist, right? Because as I demonstrated, most of the problems that we have are related to the technology of building quantum computers. So the problems are with the hardware. And I'm not an expert in hardware, so for me it's hard to say. When I talk to researchers, they are very skeptical, and they said that probably we'll have to wait for maybe even more than 10 years. When I talk to business people from companies, we can see that there is a hype. So they claim that, oh, we've already can do something very useful on quantum computers. Please, our quantum computers, please buy our quantum computers, buy access to our quantum computers. So yeah, there are many such companies. There is a hype for quantum computing, definitely. I'm a researcher, so I personally rather believe the scientists, and based on what I've seen so far in this domain, I believe that we are still waiting for a major breakthrough in technology. So all these approaches that I presented, all these approaches to build quantum computers, existing approaches, popular approaches, has some disadvantages and some serious technical challenges that has to be solved. So I think that we are still waiting for a breakthrough, but it's possible that I'm not aware of some discoveries that maybe have already happened but haven't been published yet. Because usually, very often, some companies just do some research internally, and we learn about their results sometimes even after many years. So who knows? Maybe IBM or another company have already achieved some significant breakthroughs in the technology of building quantum computers. So it's really hard to answer.
We do as AI?
Yes. Yeah, I think we should, because currently, so if assuming that we have really powerful quantum computer, will we be able to break most of the existing cryptographic codes used nowadays on the internet and everywhere? So that's why there are research works aiming to design the so-called post-quantum cryptography algorithms or quantum secure algorithms. I can tell you that there's even a contest organized by NIST, so it's the National Institute for Standardization in Technology. It's an American organization in the US. They organized a contest for the best this quantum secure algorithms. So this contest was initiated several years ago, and there were many submissions, and so we already have some good candidates. So these are just some algorithms based on the lattices of integer numbers and the problems like finding the shortest vectors or the closest vector to one of the or in the, let's say, the linear space that we have. Or there are approaches based on hash functions for just digital signatures, or there are approaches based on correction codes, or random walks in graphs, or cellular automata, or how it's called, isogeny on elliptic curves. So there are many different candidates for these quantum secure algorithms. For sure, RSA and all let's say, algorithms based on or assuming difficulty of factorization or solving the problem of discrete logarithm are not safe. So we know that we can use the Shor's algorithm or adaptation of Shor's algorithm to break those algorithms. But for other algorithms, it's really hard to say because there are almost no mathematical proof of security of these algorithms. There is a lot of work to do from the mathematical side. So there is a huge research gap still. So I cannot say that we are ready. So there are some candidates, but we are not able to prove that they are really safe. So this is one of the problems. But in case of the factorization problem, it hasn't been proven that it is safe, and we use the RSA algorithm, right? So maybe we can just use one of these candidates even without the formal mathematical proof if the proof is just too difficult for us. Maybe AI will help find the proof to one of these for one of these problems, and then we'll prove the security against quantum computers. But as for now, it's an open question. Do we have more questions? Thank you.
Thank you very much. Now, after this intense and mathematically intense lecture, let's enjoy some pizza. It will be in the back, and we will display it like right here. And there is also water, which will be provided to you. And lastly, I saw that some of you were taking pictures and videos and whatnot. I want to assure you that this presentation will be shared with you, as well as the recording, and you will have access to all the materials and all the links that are in the presentation. So thank you very much.
Thank you.
Thank you very much.
Thank you. Thanks.
Interesting.
Yeah.
Let's
I hope it was not too difficult for people, or maybe it was too easy. I think many people followed.
yeah, it was interesting. It was certainly how do I finish? Yeah.